Hi, my name is Sung-Heon from SITE in South Korea, and I'll present our paper, Procrustean Regression Network, Learning 3D Structure of Non-Rigid Objects from 2D Annotations. This is a joint work with Mi-Xing Lee from Hanyang University and No-Jung Park from Seoul National University. The main goal of this paper is to build a learning system that combines non-rigid structure from motion algorithm and deep neural networks to take advantage of both frameworks. Non-rigid structure from motion is an algorithm which reconstructs 3D shapes of non-rigid objects, such as human body or faces. Unlike rigid structure from motion, NRSfM is inherently an under-constraint problem since the object moves or deforms shape throughout the time. Meanwhile, with recent improvements in deep learning, the performance of 3D pose estimation from 2D points or RGB images have been significantly improved. However, most learning methods require 3D ground truth of training data, which is usually hard to acquire. The method proposed in this paper trains neural networks to estimate 3D structures of inputs using only 2D ground truth poses of training data. This paper is based on our previous work, Procrustean Regression. In this work, the cost function can be optimized using simple gradient descent method. This work shares similar motivations with our work in that the regularization is imposed on the aligned shapes in which rigid motions are eliminated. It was verified that applying low-rank constraint to the aligned shapes significantly improves the reconstruction performance. Our method modifies this cost function to train the neural network in a simple and effective way. The proposed framework, Procrustean Regression Network, incorporates non-rigid structure from motion algorithm into deep learning by proposing a novel loss function. At training time, the network takes inputs of 2D point sequences. Then, the network outputs the 3D shape of objects for each input shape. The predicted shapes and the ground truth 2D points are used to minimize the proposed cost function. The derivative of the cost function with respect to the 3D shapes are calculated, and the gradients are depropagated to train neural networks. PRN can also take sequences of RGB images. In this case, CNNs directly estimate 3D shapes from RGB images. During the test time, 3D shapes can be obtained by a simple feed-forward operation in a single-frame basis, without requiring any post-processing step for 3D reconstruction. The cost function of PRN consists of a data term and a regularization term. The data term corresponds to the reprojection error between the reconstructed 3D shapes and the ground truth 2D points, while the regularization term minimizes the rank of the aligned 3D shapes. The derivative of the cost function with respect to the 3D shapes is analytically derived so that the network can be trained in an end-to-end manner. Here, the aligned 3D shapes X tilde is calculated from Procruste's alignment. The aligned 3D shapes are obtained by multiplying rotation matrices to the reconstruct 3D shapes. This alignment constraint is integrated while calculating derivatives of PRN. We can use any types of data term and regularization term as long as they are differentiable. Since the cost function is a function of 3D shapes, we only need the derivative with respect to the 3D shapes to minimize the cost function. Using the chain rule, the derivative consists of 3 terms. The first term represents the derivative of the data term. We assumed orthographic projection in this paper, and the data term is defined as the reprojection error with weight or confidence for each point. Second, the regularization term is defined as the nuclear norm of the aligned shapes to minimize rank of the aligned shapes, where the derivative of the nuclear norm can be calculated using singular value decomposition. The last derivative term can also be analytically derived. Please refer to the paper and the supplementary materials for detailed derivations. We can freely choose any network structures for PRN. In this paper, we used simple fully connected networks with raised blocks for 2D pose inputs. And we used ResNet 50 followed by fully connected layers for RGB inputs. We applied PRN on 3 datasets to reconstruct 3D human poses, 3D human faces, and dense 3D human meshes, all of which are the representative types of non-rigid objects. Our method showed superior performance to state-of-the-art methods on all datasets. We measured the performance using mean per joint error or normalized error depending on the dataset. It is shown that PRN accurately reconstructs 3D shapes of human bodies from various challenging 2D poses. And PRN also effectively reconstructs human faces and dense human meshes from 2D inputs. Also, PRN can be applied to CNNs with RGB inputs without any modifications. The trained models directly estimates 3D shapes of human bodies or faces from RGB images. More details can be found in our paper, and the code will soon be publicly available. Please come by our Zoom session if you have any questions. Thank you.